Hello, good evening, good day. Welcome to the Ask Abhijit show, episode 122. Today we discuss science, technology, physics, astrophysics, all of that good stuff. I hope you're all doing very well. And let me see who all is there with us. I can see a lot of people have already joined the live stream. I can see Deepak, Navnoor, Divyang, Kuhu, Prashant, Tejas, Samarth, Virat, Darshan, Vinayak, Kedar, Manu, Alpha, A, Sayan Kumar, Dhruv, Priyanshi, Purobi, Challenge Accepted, Crazy Brain, Durga, the Akvon, Adarsh, Chiching, Shashank, Swapnil, Math Nerd Teaches Physics, Abhay Rana, Raghav, Johnny, Asmenor, Laksha Sharma, Akhil, D. Mall, Karan, Andrei, Komal, Sikha, Guy Fawkes, Darshan Patil, Amay, and lots of other people. Good evening, good day to all of you. I hope you're doing fantastically well, just the way I am. All right. Let us get into the questions. What do we have for today? A whole bunch of questions. Let's get into question number one. Question number one is by multiple people. Multiple people have asked me this, so I've taken just two questions to represent what people have asked. Lots of people have asked me about this. So, Abhimanyu says, recently it was recorded that the Earth's rotation was faster and the Earth completed 24 hours, 1.59 milliseconds in that much less time. If this continues and the Earth's rotation time gets accelerated significantly, what will be the effects on us or on the solar system? Swapnil says, is it true that the Earth is spinning faster than ever by the day and it's making our days shorter? Okay. So recently it's come in the news that apparently in 2022, a few days have been recorded that have been quite comparatively shorter than days that have been recorded in the past. And one of the days that was recorded was the shortest day ever, and it was 1.59 milliseconds shorter than the average time it takes for the Earth to complete one rotation. So the Earth, on average, takes 24 hours to complete one rotation. We know that. So that works out to 86,400 seconds, I think. And out of these 86,400 seconds, there was 1.59 milliseconds less in the time it took for the Earth to complete one rotation. So what does it mean? Well, so let's take a bigger picture approach. Yes, in the past, the Earth used to rotate much faster. About 1.5 million years, 1.5 billion with a B, billion years before present, the rotation time of the Earth was less than 19 hours. In the past, it was likely even shorter. So if you look at the large scale picture, it's clear that the Earth's rotation is slowing down, right? So imagine you're somebody who trades on the stock market. If you look at the stock market graphs of various shares over a 10-year period, you see a very clear trend, and you see trends for companies that have existed for a long time. But if you look at the share prices hour by hour, you're gonna see very what seems to be random fluctuations. So if you see it in the larger, bigger picture, in that context, the trends or patterns become apparent, and what you see on short time scales is not necessarily something that will contribute to the long term picture. But it is indeed true that this has happened. So why has this happened? Is it something that we should be concerned about? No, we don't need to be concerned about it. What if this trend continues for the short foreseeable future, then maybe we will have to readjust the way we measure time. I mean, we would have to perhaps introduce a leap second in order to make up for the shortfall of all the shorter days and all that. So that could be a headache for programmers, for systems analysts, systems people who maintain systems, and things like that. That could certainly be a headache for them. But for us, life goes on. It doesn't make any difference. Over the past 1.5 or 2 billion years, the Earth's rotation has been slowing down. So what are the factors that contribute to this? The major factor that contributes to the slowing down of the Earth's rotation is the tidal effects caused by the moon. So the Earth has a satellite, the moon. Yes. Imagine this red pomegranate is the Earth, and this yellow lemon is the moon. So the moon goes around the Earth, and it tugs on the Earth, right? It has a gravitational pull on the Earth, and this has the effect of slowly, over a very long period of time, slowing down the rotation period of the Earth. So that is the large scale thing. And also we know that the moon causes tides on the Earth. It deforms the Earth's crust. It bulges. The Earth's crust is not entirely spherical. It is oblong. It's like squash. It's like a squashed circle, kind of. Yeah. There is a bulge along the equatorial line. So the Earth gets deformed by the gravity of the moon. It's a very small, almost imperceptible change, but that's something that happens. The gravity of the moon also affects the oceans. The oceans slosh around. The planet is more than 70% water, so this water sloshes around. That also affects the rotation of the Earth. The atmosphere itself is a fluid. It also sloshes around in a way that also affects the rotation of the Earth. Inside the Earth, we have a molten interior. We have magma, an enormous pool of magma. Yeah, spherical, and with a solid core at the center, most likely. Yes. So this magma, that also is a fluid. It's a very viscous, thick, and very hot fluid that also sloshes around. That also has currents. It circulates. It's what generates the Earth's magnetic field. So the Earth is an extremely complex system. There are billions, maybe trillions of parameters that you have to take into account in order to understand why things happen the way they do, right? So that's the situation. That is what we have. That's the planet we are living in. That's what we have lived on, and over the past 2 million years, us as a human species. Yes. So this is not a cause for concern. It's not going to suddenly in a few years shorten the day. This is a very small change. Over a large period of time, the day is going to get longer, actually. So in the future, as the day gets longer, as the moon recedes from the Earth, solar eclipses will end. You will have partial solar eclipses, but the total solar eclipse that we experience today is not going to happen in the distant future. So that's the kind of thing that's in store for us in the very distant future. The thing about us is that human life is very brief. It's the human life is ephemeral from a geological standpoint. From that perspective, it's an eye blink of time. So we think that 100 years is a big deal. That's nothing in the larger picture. So that's why we are worried about milliseconds and microseconds, which don't really make any big difference in the larger scheme of things, right? So that's what's happening. And why has the Earth been rotating slightly faster in the past in recent times? We don't quite know why it's so. Like I said, there are lots and lots of factors that go into this. Most likely it's because of something to do with the tides. So the way the tides have been sloshing around on the planet, somehow that seems to have made the planet temporarily rotate just a little bit faster, 1.5 or so milliseconds faster than average, but over a long period of time it's going to actually get slower. So this is something that has happened, this is something we observe. Maybe we need to in our systems, in our computer systems, in our timekeeping systems, we need to account for this change, maybe throw in a leap second if required. So that could be a headache for programmers, for systems, for people who maintain systems and all that. But otherwise it's not a big deal, it's not an issue. This is just part of nature. That's how nature goes. All right. So this is a phenomenon you see everywhere, not just on the earth. Every single planet that has atmosphere, that has an internal magma pool, magma layer, etc., all these planets, even moons, their period of rotation changes, it varies. Or if they have multiple moons, the moons could affect that. If there's a single moon, then even then there is this phenomenon that happens. So that is what's going on. It is not something that is going to make much of a difference to life on earth. And yeah, so that's where we are. Let's take question 2. Mayuk says researchers at Yale University have been successful in restoring cellular and organ function in dead pigs. Is this a major advancement? Can it revolutionize medicine in a way? Although PETA has criticized it. So I don't know what PETA has said or not said. I'm not concerned with that. Let's talk about this interesting piece of news. So yes, I did see this news recently. So what happened is that in the past, I think in 2019, what they had done is that they took pigs, they removed the brains, which obviously necessitates killing the pigs. They removed the brains and kept the brains outside the pig body, which means that the brain is starved of oxygen, right? For an hour or maybe 4 hours or something. And then they ran some fluid through the brain, some kind of fluid that they've designed, which is mixed with the blood of the pigs. And they were able to, in some way, revive some of the electrical activity in those disembodied pig brains. So there is something that they had done in 2019. So now this year, what they have done is that they have taken entire pigs without removing the brains, and they acquired these pigs from some livestock company. They monitored the pigs for a few days, maybe 3 days or so, to see that they are stable, the vital signs are fine and all. Then the pigs were sedated, anesthetized, put to sleep, but still alive. Then cardiac arrest was induced by administering an electrical shock to the pig hearts, which results in the pig's death. Yeah, so the pigs would die. Then the pigs were left alone. The dead pigs, once the heart stopped, were left alone for about an hour or so. And then this special solution that the researchers have developed, that special solution was run through the pigs' bodies, mixed with the pig's blood. And even after an hour had elapsed, once the pigs died, and then this solution was administered, what they saw was that there was some revival of activity, cellular activity, and activity, I think, in the pig hearts and kidneys, I believe, and possibly liver also. Some sort of activity resumed, cellular activity. So what happens when an organism dies is that as soon as an organism dies, which is typically taken as when the heart stops functioning, so when there is cardiac arrest, the final cardiac arrest, the heart stops functioning, what happens is that the blood stops flowing in that organism, in that animal's body. When the blood stops flowing, the cellular tissues, all the organs are immediately starved of oxygen. We breathe in, that process is what oxygenates the blood. The oxygen is mixed into the blood via the lungs, and it is pumped through the body via the heart. That's what happens. So once an organism dies, once an animal dies, the organs and the tissues and the cells are very rapidly, in a matter of minutes, starved of oxygen. This is essentially cellular death. And as soon as the normal functioning of the organs and the cells ends, it is terminated. What happens is that there are enzymes within the cells that start digesting the cellular walls of the cells, which essentially is the process of decomposition. So decomposition starts very rapidly, within minutes of an organism dying. That is what we know. That is what we know through biology, through research. And yet, even after an hour had elapsed, after the pigs their heart stopped beating, they were able to revive some sort of cellular function in the cells, the tissues of the pigs, and even in organs like the heart, I believe, and even the kidneys, possibly the liver. I don't remember exactly what it was. So that's what they were able to achieve. uh, they did not detect any electrical activity in the brains, which could possibly be because of two reasons. First of all, the solution they had injected into the pigs' bodies, which revived the pigs to some extent. That solution was at a lower temperature than what the pig's blood would be. So maybe that lower temperature ensured that the brain did not show any electrical activity, and maybe there was some anesthetic also in that solution, which could have suppressed any activity that would otherwise have happened in the brains of those pigs. So maybe in the future they could tweak the parameters, keep the maybe uh, remove the anesthetic component from the fluid, and maybe elevate the fluid to the average normal pig blood temperature, and maybe that could possibly even demonstrate some activity, electrical activity in the brains, right? So in this experiment, they were able to see heightened cellular activity and organic activity, which kind of and when certain and they also observed involuntary twitching of the pig's necks and various other muscles when this happened, when they injected the solution. So this does uh, this is indeed a kind, you could consider this to be a landmark experiment, that even 1 hour after cardiac arrest, the pigs were revived to some extent. The brains were not revived, but maybe in the future they may be able to uh, revive some activity in the brains also. So this brings into question, that this raises questions about what is the exact definition of death. uh, there are multiple definitions from the medical perspective of death. The standard definition is cardiac arrest. When the heart stops beating, that is when the animal or a person is that is recorded as the time of death, when the heart finally stops beating. But we know that in certain cases, people who go into comas, their heart stops beating, they can be revived after 10 minutes, even after 20 minutes. That has happened multiple times, especially when a person, let's say, drowns in very cold water. Even 20 minutes after drowning, because the water is so cold, it stops decomposition, keeps the organs and the brain, etc., reasonably intact. And even after 20 minutes or so, it's happened multiple times that a person could be revived and the person went back to life as if, and they were able to resume normal life afterwards. uh, so cardiac arrest is one definition of death that is typically recorded as the time of death. The other definition is that the cessation of brain activity, all electrical activity in the brain. So a person could be alive, the body could be functioning, the heart may be beating, but there is zero brain activity. So that is brain death, right? A person who's brain dead or in a vegetative state. So there are multiple definitions of what death actually is. Yeah. So when a person is brain dead, you are allowed to donate their organs. The family members, immediate family, are allowed to go ahead and donate the organs, because the person's brain no longer exists. There is no consciousness. It's just a vegetative state. Now this experiment raises questions about what exactly death is. Even after 1 hour of cardiac arrest, they were able to revive some function in the organs. In the future, they may, who knows, in the future they may be able to revive much more of organ function, possibly even brain function, which would then raise significant ethical issues, etc., about what death actually is. I mean, is it that we are uh, we are uh, we are certifying somebody dead prematurely? Is that the norm that we've been following? Yeah. So it's still something that needs to be researched. It's still something, a lot of research needs to be done about this. But yes, it raises interesting questions. It raises somewhat troubling questions about what death actually is. So yes, more research needs to be done in this. The research will be done, because it's the what people call the holy grail, right? Coming back from death. So if that sort of thing could be done, it could revolutionize medicine, and people would possibly never ever die if you take it to the ultimate conclusion. So that's what's happening. That's where we are. That is the experiment. And it's still a work in progress. It's not a final result. It's just maybe one of the initial steps in a long journey. Yeah. So that is what this experiment is about. And they are going to continue the research in and take it forward. Sudeshna says, what's the difference between a cheetah and a leopard? Because although cheetah has been extinct from India, a lot of people tend to confuse between the two. Moreover, which one of the two is more dangerous than the other? Do you think that while doing science, everything mentioned in fact must be taken literally with the literal meaning only? Let me take the cheetah versus leopard question. I'm not sure what the other question is, right? So, what's the difference between a cheetah and a leopard? Well, leopards, I think, are much more powerful. And if you look at the face of a cheetah and a leopard, they are both cats. Yes, of course. The cheetahs have this signature marking on the face that it's like tears, black tears. Let me just put that on the screen so that you can see the difference between a cheetah and a leopard. All right, let's Google cheetah. What does a cheetah look like? So let's see the cheetah's face. Cheetah face. So there you have the face of a cheetah. As you can see, there are these the signature markings on the face that look like flowing tears, but it's black. These are black markings. Here's another one. So all cheetahs have this black marking, and as you can see, cheetahs have these slender and long bodies. They are the fastest animals on the planet. They are quite delicate, actually, cheetahs. And cheetah versus human. Let's see the scale, cheetah and human. So as you can see, this is the size comparison between a cheetah and a human being. This is yeah, that's what it looks like. So it's a medium sized cat. It's much larger than our standard house cats or domestic cats. It's much larger, but compared to other cats, the cheetahs have slender bodies and are somewhat delicate. What does a leopard look like? And cheetahs cannot roar. They are not able to produce that roaring sound. Cheetahs sound like house cats. They meow, meow, meow. That's what they do. Leopards can roar, and they are much more strongly built. They don't have those markings on their face. They've got spots. Leopards have spots. Yeah, this is a comparison between the cheetah and a leopard. And leopards are much more dangerous, in my opinion, than cheetahs. Cheetahs also are obviously, they are wild cats. They are large cats. They are dangerous. But leopards are way more powerful, physically stronger than cheetahs. And stockier. The build is different, as you can see. So leopard versus human. Let's see this size difference. Okay, these are very unfortunate images, but leopard, humans. Okay, so this is the size difference. This looks like a snow leopard, which is one of the varieties of leopard that we have in India, in northern India. So leopards look like they are somewhat smaller than cheetahs, but they are way more powerful than cheetahs. Okay, let me not show such images here. That's kind of. All right, let's go back to the leopard. So that's the difference. Leopards can roar, cheetahs cannot roar. Leopards, the face doesn't have those tear markings. Cheetahs, they do have it, right? And leopards are somewhat smaller, but they are way more powerful than cheetahs, way more physically stronger than cheetahs. And of course, the Indian cheetah is extinct, but we are reintroducing the cheetah into India. We are acquiring cheetahs from South Africa as well as Namibia. So that is what is the most recent developments. So I believe the cheetahs are slightly shorter and stockier than sorry, I believe leopards are slightly smaller in size than cheetahs. Cheetahs have a longer body, but cheetahs are more delicately built. They are built for speed, not for strength and power. Leopards are stronger. They can take a deer by its neck, clamp it in their jaws, and lift the deer, which may actually be larger than the leopard. They can lift it all the way up to a tree. That's the kind of incredible, immense physical strength that the leopards have. Cheetahs are not quite that strong. Leopards are very hard to domesticate and tame. You can't domesticate any of these large cats, but you could kind of tame some of them. Cheetahs are almost like house cats. If you raise a cheetah from the time it's a kitten, It's going to be just like a house cat. It's not going to be that dangerous. Leopards are a whole different story. You will not see any YouTube videos of people having a leopard as a pet, but you may see humans having cheetahs as pets, or caracals, or other wild cats. So that is the overall difference between cheetahs and leopards. Cheetahs used to be abundantly available in India. You had cheetahs everywhere. They were almost like cats here. The Turkic emperor, what was his name? Jahangir, I think. I believe he had 5,000 pet cheetahs in a menagerie or whatever. So that's how abundant cheetahs were in India. A couple of about 3-4 centuries ago, they were decimated by the British, and that's what happened. Now we are reintroducing them. Leopards, we still have them in India. Leopards, yeah. So which one is more dangerous? Definitely the leopard. The leopard is much more dangerous. Yeah. So that is the answer to this question. Okay, the question is, why do different sizes of black holes exist? And what do you mean by different sizes of infinity? Yes. Uh, okay, let's first talk about black holes. Well, stars come in different sizes, planets come in different sizes, galaxies come in different sizes. Similarly, black holes come in different sizes. A black hole may be born from stellar collapse from a star that is, like, let's say 20 times the mass of the sun. Yeah. But if it is in a dense neighborhood where there are lots of clouds of gas and other stuff, it may then swallow all that gas and grow larger over time, larger. Yeah. If you have a black hole that's at the center of a supermassive if you have a black hole that's at the center of a galaxy, most galaxies have supermassive black holes at the center. In some cases, these black holes are active black holes. They're actively swallowing more mass, clouds of gas and dust and stuff. Those black holes will grow over time. So that's why you have black holes of different sizes, different masses. Some stars that collapse into black holes do so at the end of a supernova explosion. Some stars simply collapse overnight into black holes. One day it's there, the next day it's all dark. What happened? Where did the star go? It winked out and became a black hole. So there are different processes through which black holes are formed. Black holes could even have formed in the very early universe, the primordial universe. Those are the hypothetical primordial black holes, which may be very small. We have never observed any, but it's certainly allowed by physics. Yes, maybe there could have been lots of primordial, incredible amounts of primordial black holes that were formed. Maybe they could form some part of dark matter, or bound states of primordial black holes may be a component of the cold dark matter that we know exists in the universe, and so on. So that's why black holes come in different sizes, all right, different masses, and so on. Now, what about the different sizes of infinity? Now, this is an interesting question, and to explain this, I should show something on the screen. I am sure you all know what a number line is. Yes, what's a number line? Let me put a number line on the screen, with which I shall demonstrate that infinity comes in different sizes. So here we have a number line. We have three number lines. Let's take a look at the topmost number line, which goes in both directions. It's from 0, 1, 2, 3, 4, all the way to 10. And the arrows indicate that the number line goes on up to infinity in both directions. So 10, 11, 12, etc. And from 0, if you go to the left, it is 0, -1, -2, all the way to minus infinity. Right? That is number line number 1. Now let us take, so essentially between 0 and 10, how many numbers do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 4 numbers. Now, let's take the space between 0 and 1. You can construct a number line between 0 and 1 as well. And you have the decimals, right? 0.1, 0.2, 0.3, all the way to 0.9, and then 1.0. Now, let's take the space between 0 and 0.1. Between that, you have a whole different number line, 0.01, 0.02, and so on, all the way to 0.09 and 0.10. And you can go deeper and deeper into it. Between 0 and 0.01, you will have other numbers and so on. What I'm trying to say is that between 0 and 10, you can place an infinite number of numbers. So there is an infinity. There is an infinite number of points or numbers between 0 and 10. That is infinity. You also have an infinite number of points or numbers between 0 and 1. That is also infinity. You also have an infinite number of points or numbers between 0 and zero point 0.1. That is also infinity. So we are talking about three different infinities here, between 0 and 10, between 0 and 1, and between 0 and zero point 0.1. All three are infinity, but we know that the space between 0 and 10 is larger than the space between 0 and 1. And that space is larger than the space between 0 and zero point 0.1. What does this tell us? It tells us that infinities come in different sizes. Which doesn't make sense, but when you look at the number line, it becomes clear that even though all these three quantities are infinities, they have different sizes, which means that certain infinities are larger than other infinities. And as a kid, when you first understand this concept, it kind of causes a little bit of brain damage. So, yeah, that's what we mean by different sizes of infinity. Infinity is infinite, and yet it comes in different sizes. That is the strangest thing you come across as a kid. I mean, if you ever think of it in mathematics. Yeah. So that's what we mean by different sizes of infinity. Okay, Swapnil says, can you explain the Drake equation hypothesized by the astrobiologist Frank Drake? Was it a legitimate or a failed experiment? The Drake equation is not an experiment, it's an equation. It is an equation that seeks to kind of put a number on, give us a handle or give us an approximate idea of how many intelligent civilizations exist within our own home galaxy, non-earth, non-human civilizations. So let me show you what this equation is like. It's got a number of parameters. Let us share the screen. Here it is. Yes. So this is the Drake equation. Okay. N is the number of detectable civilizations in the Milky Way galaxy, in our home galaxy. N is equal to R star times Fp times Ne times Fi times Fl times Fi times Fc times L. Now, what do those parameters mean? N is what we want to see, what we want to calculate, the number of detectable civilizations currently exist in the Milky Way galaxy, in our home galaxy. R star is the rate at which stars are born per year. How many stars are born in the Milky Way per year? Let's say it's 1, let's say it's 10, whatever the number is. So we will have to, so that is the meaning of R star. What is Fp? It is the fraction of stars that hosts planets. So let's say you take any random 100 stars in the Milky Way at random. How many of these stars have planets? So that is the fraction that we're talking about, right? The fraction of stars that host planets. Ne is the number of habitable planets per planetary system. Yes, so out of these stars that actually have planets, how many of these planetary systems or star systems have planets that are actually habitable? Like Earth, like what it means is how many of these have Earth-like planets? That fraction. Fl is the fraction of those planets on which life actually evolves. And that is something we have to completely guess because we have never found life anywhere except for Earth. But we may be able to arrive at an intelligent guess as to what is the fraction of those planets on which life evolves. Fi is the fraction of life that evolves intelligence. Fc is the fraction of intelligent life that becomes communicative, that develops communicative technologies. And L is the average length of time that civilizations are detectable. So if you multiply all these parameters together, it gives you N, which is the number of detectable civilizations that currently exist in the Milky Way galaxy. Now, a lot of these parameters are simply guesswork. We can calculate R star reasonably accurately. Maybe it's around 1 star per year or 10 stars per year, somewhere around that. Fp also, because we have now a lot of observational data, it looks like the fraction of stars that host planets could be close to 1, 0.5 or 1 based on how many we have observed. We know there are lots of exoplanets out there. It looks like planets are very common. So it could be close to 1, the Fp. Ne could be around 0.1 or so, maybe 0.2. I'm just guessing here. Yeah. FL, we don't know. We don't know. Let's say it's 1, or let's say it's 0.5, whatever. That's another guess. Fi is absolutely conjectural. We have no idea of knowing, but we could put in a number just to see how it works. Fc also we don't know, and L is again guesswork. So as you can see, this is an equation that involves a lot of guesswork. You plug in different values for these parameters, you get very different, wildly different values of n. N is the number of detectable civilizations that currently exist right now, as of today, in the Milky Way galaxy. Right. So this is not an experiment. This is an equation that serves as the beginning of a conversation. Yeah. So I think it was developed as part of the SETI project. SETI is Search for Extraterrestrial Intelligence. So when this project started, which sought to detect signs of intelligent life in other parts of the galaxy and other galaxies possibly, uh, the scientists wanted to have some kind of a number as to how many, as to how common or uncommon or rare intelligent life could be in our galaxy. And that is what gave rise to this equation. And as you can see, we don't have hard numbers that we could plug into this, so a lot of it is guesswork. And based on this guesswork, the number of the value of n ranges from 1 to thousands possibly. So that's how it is. But it's an interesting conversation starter, and it's something that people discuss from time to time. So that is what this Drake equation is. It's not an experiment, it's an equation which seeks to kind of give us a handle on how many intelligent civilizations could currently exist in our home galaxy. Romit says, what is your take on the Fermi paradox? Okay, what is the Fermi paradox? The Fermi paradox could be asked in the form of a question. Where are all the aliens? Right? There are so many stars in our galaxy. How many? 100 billion? I believe it's 100 billion plus, give or take. Those many stars in our home galaxy, the Milky Way. 100 billion, let's say. How many galaxies exist out there? I believe hundreds of billions, maybe 200 billion galaxies in the known universe, possibly. Yeah. So if you calculate, and let's say all galaxies have approximately the same number of stars, the Milky Way and so on. So if you calculate the number of stars in the observable universe, it's about 10 raised to 23 or 24. One with 23 or 24 zeros after that, after it, give or take, right? That is an incredibly large number of stars. I mean, it's hard to conceive such a large number. So if you have so many stars in the observable universe, is it not likely that there will be life out there? That life could be quite common. There could be billions, trillions of intelligent civilizations out there, right? It should be quite common, given the enormous number of stars that exist in the observable universe. So if should be that common, statistically speaking, if life should be that common, then where are all the aliens? Where are they? Why don't we see any of them? That is the Fermi paradox. That is the question that I believe Enrico Fermi asked to his colleagues. That's the Fermi paradox. Statistically speaking, life should be common. So if it is common, why don't we see any signs of life anywhere? That is it. And there are lots of different possible answers to that. One answer is that life is not common. We are the only life out there in the entire universe, which makes us incredibly unique. That is one possible solution to the Fermi paradox. The other solution is that life is everywhere, but it doesn't want us to see it. There is something called the zoo hypothesis. The Earth is a zoo, and we are being observed, but we have no idea we are being observed. Think of it like this. Think of a petri dish in which you have microbes, a colony of microbes, a few million microbes, or let's say 8 billion microbes living in a petri dish. This petri dish is in a lab, and scientists are observing it through a microscope. And in this petri dish, these bacteria, they're talking to each other. We are so intelligent, but we see no life out there. Where is all the life? Yeah. and they have no idea that they are currently being observed. So maybe there could be intelligences out there that are so highly advanced that compared to them, we are like little bacteria. Yes? And we have no means of knowing that we are currently actively being observed and studied. So that is a possibility. The zoo hypothesis. There are various other possibilities. There is the great filters hypothesis, that life could actually be common, but there are certain hard barriers that life encounters that ensures that we don't get to see that it exists. Maybe intelligent life has a tendency to destroy itself. We have developed various technologies that are very dangerous, nuclear weapons, etc. Maybe in the future we may run into a great barrier, a nuclear war which annihilates everything. That is a possibility. Or sends us back to the stone age. That's a possibility, right? Or there could be certain cataclysmic events, that kill off life every few million or billion years. That is also a possibility. Extinction events, global catastrophes, cataclysmic events, like there are lots of astrophysical events that could end life, right, on a planet. So that sort of thing is there. uh, maybe it may be the case that once a civilization reaches a certain stage, it transmits information for a certain time period, and then the transmissions stop. So we still have radio waves which go out into space, but eventually our technologies will become so effective that efficient that we will not have to broadcast radio waves into the atmosphere and into space. We may be able to communicate without doing that. So we may stop transmitting, right? So maybe in a century or so, we may no longer be transmitting the way we were transmitting in the 20th century, and even right now. So maybe intelligent civilizations transmit only for a century or two, and then all transmissions stop. That is a possibility. There may be a possibility that intelligent life is common, but it is very dangerous to other intelligent life. And that's why all intelligent civilizations try to hide themselves. I think it's called the dark forest hypothesis. Let's say you are traveling in the night through a forest. It's a dark forest, right? Now, we know that in this dark forest, there are other animals. Some could be nice, but there could be tigers, there could be leopards, there could be pythons, there could be crocodiles, and various other things. So, what is the optimum way of being in a dark forest? Try to stay hidden. You may encounter an animal that is harmless, but you may encounter an animal that may terminate you. So the optimum solution is to assume that all life that exists in this dark forest is out to kill me. Be extraordinarily paranoid and hide yourself. That is the best um, optimum solution for survival. So there is a dark forest hypothesis that all intelligent life assumes that any other intelligence it encounters is life threatening for it, and that's why you hide yourself. You don't transmit, you just stay hidden. So there could be lots of other civilizations out there, but they are not stupid enough to broadcast their location. And that kind of tells us that we should not be stupid enough to send radio waves into space and broadcast our location to various stars, like some astronomers and scientists have done. That may be a very, very, very bad thing to do, and so on. So there are different such theories, hypotheses that have been put forth. We don't quite have the solution right now, because thus far we have not found any sign of even non-intelligent life beyond our home planet. There are potential locations in our own solar system where microbial life or lower level life could exist. Places like Venus is a possibility. Mars is a possibility. um, the moon Europa, the moon Titan, etc. There could be other places in our own solar system where life could exist. There could be a subsurface ocean on Pluto itself where possibly life may exist. If it is liquid water, then it is warm, reasonably warm, and life could exist there. So there are lots of possibilities. So if we are able to find life somewhere else in our own solar system, first of all, that could indicate that life could be really very common out there. And that's why, and then if life indeed exists elsewhere, it means that a certain percentage, certain fraction of that life becomes intelligent. Like in the Drake equation. There is a fraction. There is a term for that. Let me put that back on the screen. Here is the Drake equation. The fraction of life that evolves intelligence, Fi. So there would be, once we know that life does exist elsewhere, then this term Fi comes into the picture, and so on. So there are different hypotheses. We don't quite know what's going on. We are still like those little microbes in a petri dish. Yeah, we may think that we are hyper intelligent and all that. We have all this technology at our disposal, all this science at our disposal, and yet we may be like those microbes compared to other hypothetical intelligent beings. Yeah, so that is what the Fermi paradox is. Abhishek says, what orbit does the James Webb Space Telescope follow? Does it orbit the Earth or the Sun? The James Webb Space Telescope is orbiting the L2 Lagrange point. Now, what is a Lagrange point? What is this thing? So, we have the Earth-Sun system. Let me bring in my fruits again. So, imagine that this pomegranate, red, is the Sun. Imagine that this little yellow lemon is the Earth. So we have the Earth-Sun system. The Sun is large. The Earth is way smaller than the Sun. All right? Both have a gravitational attraction, and the Earth goes around the Sun in an orbit, right? So if you look at the gravitational pull of the Sun, which is much larger than that of the Earth, and let's say you have a third object that you want to place between the Earth and the Sun, there will be, and if you draw a straight line between the Earth and the Sun, there will be a place on the straight line where the gravitational pull of the Earth and the Sun cancels each other out, and that object may be able to remain indefinitely in that place. That is the L1 Lagrange point. Let me show you an image, a schematic of this. What do these Lagrange points look like? There are 5 of them. Here we are. So the L1 Lagrange point is the point between, it's an equilibrium point between the Earth and the Sun. It is not quite stable. It is what's called a metastable Lagrange point. There is another point called L2, which is in the same straight line, but it's behind the Earth. So in the straight line between the Earth and the Sun, behind the Earth, there is another equilibrium point called the L2 Lagrange point. And that's where the James Webb Space Telescope has been parked. Other telescopes have also been parked there, like the WMAP telescope, Wilkinson microscope, microwave anisotropy probe, WMAP, I believe it's called. Then there is an L3 point that is behind the on the other side. So if you take a straight line between the Earth and the Sun, then on the other side you have the L3 point, and then you have the 2 equilateral triangle points, L4 and L5. So if you take the Sun, the Earth, and L4, that forms an equilateral triangle. And similarly for L5 also, we have an equilateral triangle. The L4 and L5 Lagrange points are reasonably stable. They are not metastable, they're actually stable. You put something there, it will stay there. But if you put something in L1 or L2 or L3, those points are kind of metastable. So you need to spend a little bit of energy, a little bit of fuel to keep that spacecraft in that point. In the future, you may have spacecraft, even space stations, stationed at these points. Maybe in 100 years, maybe in 200 years, if we do well, if we evolve our technology further, we may have spacecraft, space stations sitting at L3, L5, especially at L4 and L5, right? So these are Lagrange points, and that's where, and especially at L2, that's where we park spacecraft. It's not very stable, so the spacecraft needs to have some fuel, small rocket engines, to periodically adjust the orbit so that it stays in place. So the James Webb Space Telescope is not exactly at L2, it is orbiting the L2 Lagrange point. So these points are called Lagrange points because they were first calculated by a guy called Lagrange about 200 or 300 years before today. Look it up if you're interested when exactly that happened, right? He was a mathematician. So that's what it is, right? That's where the James Webb Space Telescope is parked in orbit around the L2 Lagrange point. It's interesting that it's not only the Earth that has Lagrange points. Even the Earth-Moon system has Lagrange points, but that is kind of messed up by the enormous gravitational pull of the Sun. Jupiter has Lagrange points. The Jupiter's Lagrange points are called the Trojan points. So if you look at imagine instead of the Earth we have Jupiter. The Jupiter will also have all the same Lagrange points, but in the case of Jupiter they are called the Trojan points. And in the L4 and L5 regions of Jupiter we have these, I don't know, thousands or millions of asteroids that clump around that place. They are called the Trojan asteroids, right? So Jupiter is like a shepherd, and the sheep are all these millions of Trojan asteroids that clump in the Lagrangian points of Jupiter. So that's a natural phenomenon that we observe. So that is what the Lagrange points are, and that is where JWST is parked in orbit around the L2 Lagrange point. Vishal says, what is orbital eccentricity? All right. What is, first of all, forget about orbital eccentricity. What is eccentricity from the point of view of geometry? So, in geometry, we all know what a circle looks like. It's a circle. We also have something called an ellipse in geometry. It's a conic section. Let me put that on the screen, conic sections, so that you actually get to see it. Conic sections, and let me put that on the screen. Give me a second. Here we are, conic sections. No map today, only conic sections. Here we are. All right. These are conic sections. So if you take a cone and you slice it up, that's what we get. We get circles, we get ellipses, we get parabolas, we get hyperbolas. And each of these guys has its own equation, and you can study it if you're interested, right? Conic sections. So a circle is perfectly circular. An ellipse is like a squashed circle. You take a circle and you squash it, you get an ellipse. So an ellipse has something called eccentricity. Let's take a look at eccentricity of ellipse. All right, so every ellipse has a certain eccentricity, which is part of the formula, which is C by A, and so on. Now let me show you the eccentricity of orbits. Orbital eccentricity, right? Orbital eccentricity. So orbits are like ellipses, and here is an example of orbital eccentricity. Let me put that on a different page and show you that page so that you get a better idea of what it is. So the orbits of the various planets, etc., around the sun are not perfectly circular. They are elliptical orbits, and that's what it looks like. So, based on the different values of the eccentricity, we get these different shapes of ellipses, and the same goes for satellites. You could have satellites in a circular orbit. You could have satellites in squashed, elongated elliptical orbits, and each orbit has a certain value of its eccentricity, and that's what orbital eccentricity is. All right, so it's all about geometry. You study geometry, you will immediately understand what eccentricity is. Now let me show you the various orbits. Let me quickly show you what elliptical orbits look like in the solar system. So in the solar system, none of the orbits of the planets is perfectly spherical. Let's take a look at this. So there is a hypothetical planet 9 and various other objects in the solar system. They all have orbits with varying eccentricity, right? So that's what we mean by orbital eccentricity. All right, hope that makes sense. Right. Moving on to the next question. Brown Nerd says, since only about 5% of the oceans have been explored, do you believe there's intelligent life deep in the oceans? Beings such as mermaids and mermen and merbeings, right? I believe it's indeed true that we have explored next to nothing of the oceans. The oceans are almost completely unknown to us, right? Light penetrates the ocean about to a depth of about 100 meters. So if you go below 100 meters into the ocean, it's all dark. There's no light at all. You have bioluminescent fish and organisms, etc., but that is few and far between. So the vast amount of the ocean out there is dark. There's no light, and we don't quite know what lurks deep beneath the surface of the oceans. We have submarine cables and all, which we've been able to lay. We have sonars that tell us what the surface of the ocean looks like. Yeah, we have submarines that make use of these undersea features that navigate through them. We have detailed maps, topological maps of the subsurface, sub ocean surface of the earth, and so on. So we have some idea, but we haven't actually been there and seen what kind of life is there. So it is possible that there could be lots of unknown species that lurk in the deep depths of the oceans. Yes, indeed true. People speculate there could be certain varieties of dinosaurs that may exist. They may have evolved the ability to to do that without oxygen, to have gills or whatever, possibly, and live and respirate the way fishes do, etc. So it is very likely that there could be a large number of completely unknown species of fish and other marine life that we still haven't encountered or discovered thus far. That is certainly possible. That is a fact. It's there. We discover new species every year. Marine species. That happens all the time. When it comes to intelligent life, I believe it's unlikely. The probability is low. It's not zero. The probability is not zero, but I think the probability is low. Why do I say that? Because intelligent life, one of the hallmarks of intelligence is curiosity. If you are intelligent, you're going to be curious about what else is out there. And you may travel, you may venture around the oceans. And if you travel, if you venture, if you go to new places, you will be discovered. So intelligent life has this tendency to be discovered, to make itself known. Yeah. But on the other hand, if it is really intelligent, it would know that it's a wise thing to stay away from humans, because humans are aggressive and they're violent and they're destructive, and maybe they are observing us and they know that they should stay away from us. That is also a possibility. So what do I think? I believe that the probability of intelligent life existing deep under the oceans is low. It's not zero. If it does exist, then it's very smart. It knows to stay away from humans. Yeah. But there is no evidence of that. And yet it may possibly exist. The probability is low and remote. Karthik says, animals also have blood groups. When one animal hunts another animal, doesn't the prey's blood get infused in its body? Won't that cause any harm to the predator due to the entry of foreign blood? Foreign blood. So it's like this. In human beings, we have blood groups, right? And if by mistake or by accident, someone were to infuse a person with blood who has, let's say, hypothetically blood group A, and you were to infuse blood group B or something else into the person, there would be a very strong and adverse biological reaction which may cause the death of that person, the death of the recipient. So we have to make sure that we match the blood groups and we don't mix it up, right? And when it comes to the blood of other species, if you infuse that into your body, there's going to be terrible immunological reaction. You may end up losing your life, or you may end up getting really, really sick. You may have the entry of bacteria and other organisms from another species into you, and your immune system may not know how to deal with that, and that could cause all kinds of complications, maybe even death. So yes, that is there. Now, when an animal hunts another animal, let's say you have a Tyrannosaurus rex. Okay, let's not go that far back. Let's say you have a lion that hunts a crocodile in the river, right? So there's a big struggle, and the crocodile bites the lion bites the crocodile. At the end, the lion is larger and stronger. He wins. He pulls the crocodile out of the river, snaps its neck, and then proceeds to have a nice big feast, right? And of course, when the lion eats the flesh of the crocodile, the blood of the crocodile will go into the lion's stomach. Now, here's the difference. We're not doing a transfusion of the crocodile's blood into the lion's blood. We're not doing that. The blood and the tissue, etc., which is masticated, chewed, etc., goes into the alimentary canal of the lion, settles down into the stomach. It is processed over there. There are stomach acids that break down, and enzymes, etc., that break down the tissues into simpler uh, into a simpler form. It's then transferred into the esophagus and into the small intestine, where it is processed further and further and further, and that's what happens. So the blood of the animal that is preyed upon is not infused or transfused directly into the bloodstream of the lion. It goes through the alimentary canal into the digestive system, and the digestive system is equipped to handle these foreign substances. There is a purifying mechanism. The liver is the great purifier. Anything that is harmful or toxic in any way is removed, and it is filtered essentially by the liver. That's why so we have all these fail-safe mechanisms in the human body, and all animals have livers, even sharks have livers, etc., right? So that's why it doesn't cause any harm. If you were to take the blood of a crocodile and sedate a lion and then infuse that intravenously into a lion's bloodstream, that could end up killing the lion. That could cause significant amount of harm to the lion, or species X to species Y, it will cause harm, right? But as long as that animal is eating another animal, it goes through the proper channels, like they say. Yeah, if the blood and the tissue and the meat, etc., flesh goes through the proper channels, which is through the digestive system, then all is well, because the digestive system has all these checks and balances that ensure that nothing that's not supposed to go into the bloodstream is allowed to go in there. And that's how it works, and that's why no such harm ensues. Okay, Priyanka says, as we know, only 5% of the universe, that is 200 billion galaxies, are in the 5% universe. Yes, that is indeed correct. I don't know how many galaxies are there in the universe. You can Google it. Let's say it's 200 billion, maybe. Yeah, I don't remember all the numbers. So let's say there are 200 billion galaxies in the observable universe, which is a spherical ball with you at the center, right? So yes, everything we observe in the universe is actually 5% of the mass energy composition of the universe. All these galaxies, all the stars that we observe, all the dust clouds and the nebulae that we observe, every single thing that we observe in the universe, it actually makes up less than 5% of the actual mass energy composition of the universe. 95% of the universe is dark and unknown to us. We are made up of special stuff. We are electromagnetic beings. That's what we are. Light is an electromagnetic phenomenon. We see things. The reason why I'm not falling through the chair that I'm sitting in is because of the electromagnetic force and the Pauli exclusion principle, and so on and so forth, right? That's why matter has occupies space, and so on. So yes, what you are saying is correct. Everything that we observe in the entire universe is just 5% of the mass energy composition of the universe. Pulkit says, what is dark matter and dark energy? Well, good follow-up question. What is dark matter and what is dark energy? So obviously this is something I've answered lots of times, but for the benefit of those who have joined recently, for the new viewers, let me explain what is dark matter and dark energy. So everything we observe, like I said, in the universe, every single galaxy, every single star, every single exoplanet, every single gas cloud, every single nebula, everything we observe makes up only 5%, about 5%, or somewhat less than 5% of the actual mass energy composition of the universe that we live in, of the observable universe. About 68% of the mass energy composition of the universe is what we call dark energy, and about 27% is what we call dark matter. If you want to keep it simple, make it 70-25. 70% dark energy, 25% dark matter, 5% visible matter, of which we are made. So how do we know this? Oh, we were able to figure out that something called dark matter exists because of galactic rotation curves. Let me show you what those are. Galactic rotation curves. What are these things? Let's put that on the screen. Yes. So this is an example. This is a very famous graph, galactic rotation curves. So when you see a galaxy, galaxies rotate. We know that. We know that galaxies rotate around their center of mass. So when you see the amount of mass, visible mass a galaxy has based on its luminosity and various other things, we expect it to rotate at a certain speed. And yet, when we actually do the observations of galaxies all across the observable universe, we find that the rotation speed is different. It's as if there is much more mass in the galaxy than what we are seeing, right? So it is because of this phenomenon, this observational evidence, which we were able to see over and over again in all kinds of galaxies. It's because of this that we were able to figure out that there is some unseen matter that lurks around galaxies. So all galaxies have a dark matter halo, which also rotates with the galaxy, right? And that's why we have this difference in between what we expect and what we actually observe. So let me see galactic halo, what it looks like. What does a galactic halo look like? So typically a halo is more or less spherical, yeah, and all most galaxies are enveloped or shrouded in these dark matter halos. So this is one example. A galaxy is a flat kind of thing. A spiral galaxy is more or less flat. It has a galactic plane, and yet there is a dark matter halo all around it. It's more or less spherical, right? This is another interesting such picture. So that's how we know that dark matter exists. Now, what is dark energy? Dark energy. So dark matter, what it does is that it tends to it acts like a glue, right? So it keeps the galaxy together. It has an attractive gravitational force. We can deduce the existence of dark matter also through the phenomenon of galactic lensing. Let me show you what that looks like. Galactic lensing. So something in galactic lensing, objects appear distorted, as if we are observing that object through a lens. So this is a very very nice example of that. Yeah. Sometimes you see double images. Sometimes you see galaxies that look stretched out, and so on. So this indicates that there is a massive object between us and the galaxy, or the object that we're observing, and that is distorting space-time itself. Yeah, that is what general relativity tells us, and that's how we know that there is something out there, and that sometimes is an indication of a black hole, or sometimes it tells us there is dark matter over there between us and the object we're observing. So that's how we know dark matter exists. And dark matter is massive, and it has an attractive the gravitational effect is attractive. Dark energy, on the other hand, it is something that causes the expansion of the universe. You can think of dark energy like it's a fifth force in the universe. We know there are four forces: the strong nuclear force, the weak nuclear force, the electromagnetic force, and the gravitational force. Dark energy is like repulsive gravity. It actually pushes things apart. We know that the universe is expanding. We know that something is causing the universe to the expansion of the universe to accelerate. Not only is the universe expanding, this expansion is accelerating over time. There is some unknown force or energy in the universe that is causing this to happen, and that is what we call dark energy. So you can think of dark energy as a fifth force, as a repulsive form of gravity, or whatever you want to call it, and it accounts for roughly 70% of the mass energy composition of the universe. All right, so that's dark matter, roughly 25%, dark energy, roughly 70%, and visible matter, of which we are made, which is about 5% of the mass energy composition of the universe, which means we are made up of special stuff, only 5%. The other stuff, the common stuff, is invisible. We don't know what it is, but it's out there. So that is dark matter and dark energy. Krishna says, if light in the universe is about 13.8 billion years old, how can we observe the observable universe, which has a radius of more than 40 billion light years? So, the best theory that we have of the origin of the universe is is the so-called Big Bang theory. Yes, and we know that the universe is roughly 13.8 billion years old. The oldest light that we observe in the universe is about 300 million years. It's from about 300 million years roughly after the Big Bang happened. That is the oldest light in the universe. It's stretched out into the infrared wavelengths, and that's what the James Webb Space Telescope is tasked with observing. So the oldest light is about, let's say, around 13.5 billion years old. Yes. Um, so the most distant objects traveling at the speed of light would be 13.5 billion years, billion light years away from us. So the observable universe is like a sphere. Let me show you what that looks like. Observable universe. What does it look like? Well, let's take a look at a representation of that. So let's say that this is a schematic of the observable universe. Is this it? Okay, we're talking about parsecs and all that. This is a cross section of that, and so on. So what we find is that the radius of this observable universe is not 13.5 billion light years. It's actually about 45 billion light years in radius. So why is it so? So this is you can explain this quite simply. It's because of the expansion, the accelerating expansion of the universe. Because the universe is expanding in an accelerated rate, that's why it has gone so much further away. And the oldest and the furthest light that we see, even though it's just 13.5 billion years old, yet the radius or the diameter of the observable universe is so large. So the radius is about 46 billion light years. The diameter is about 90, 91, 92 billion light years, because the universe is expanding. And every single day that passes, there are certain parts of the observable universe that disappear forever. Because beyond a certain point, the expansion of space-time becomes superluminal. The expansion becomes faster than the speed of light itself, and that does not break the laws of physics. The speed limit within space-time is the speed of light, but space-time itself can expand even faster than the speed of light. And because of this, there are parts of the observable universe that every single day, every single minute, every single second are going forever beyond our observational range. Right? So that's what's happening. Eventually, in the distant future, the observable universe will be simply the Milky Way. We will be able to observe nothing beyond that. And eventually, one day, only the solar system will be left. So that's what's going to happen in the very distant future, because of the expansion of the universe caused by this strange thing called, this unknown, mysterious substance or force called dark energy. Okay, T1 says, can we get our hands on a bottle of dense dark matter? You can't get your hands on a bottle of dense dark matter, but if you have an empty bottle in your hand, it contains dark matter. Right now, there is dark matter in this room. Most likely there is dark matter in this room. The solar system, the Earth, passes through clouds of dark matter. Like I said, there is a dark matter halo that envelopes our galaxy. The visible part of the galaxy is just a small portion, maybe 10% of maybe roughly 10% of the mass energy of the entire galaxy. Around 90% could be dark matter, which means that we are enveloped in a massive halo, massive cloud of dark matter, which means there are dark matter particles right now in this room where I am, and right now wherever you are. Dark matter particles are passing through your bodies as we speak. Um, and dark matter is most likely some particle or some family or class of particles that are purely gravitating in nature. They only interact through the gravitational force and not through any of the other three forces. The gravitational force is many orders of magnitude weaker than the weak nuclear force. Solar neutrinos interact weakly via the weak force. As we speak, every second as we speak, trillions of solar neutrinos pass through our body. Right now, every second, trillions of these solar neutrinos that come from the sun are passing through my body. I don't feel anything because they interact so weakly. So, if that is the weak force, imagine how weak gravitation is. So, there are all these dark matter particles that are passing through us every single moment, and we don't realize that. You have an empty bottle, most likely there's dark matter within it, but it's passing through it. You cannot confine it in your bottle. It will simply pass through your bottle as if the bottle doesn't exist. So yeah, that's what it is. Vaibhav says, please explain what the Higgs boson is. All right. What is the Higgs boson? What is the Higgs field? So from the point of view of the standard model, the standard model of physics says, and this has been experimentally proven, rigorously tested, the standard model of physics tells us that there are 16 known elementary particles. Let me show you what that looks like. Demonstrate that. Give me a second, please. Let me share my screen and show you the standard model of elementary particles. Here we are. So we have 16 known particles. All right. We have the quarks, up, down, top, bottom, strange charm, 6 different kinds of quarks. We have 6 leptons, the electron, the muon, the tau, and their corresponding neutrinos. And there used to be 4 bosons, now there are 5 bosons. So the gluon, the photon, the Z boson, the W boson, and the Higgs boson. So these are the 17 fundamental particles that we know of. And from the perspective of quantum field theory tells us that the world that we inhabit, the world that we perceive and observe, is an illusion. What actually the universe is actually made up of fields, interacting fields. And all these elementary particles are merely local excitations in these fields. So there is an electron field that permeates, a 3-dimensional electron field that permeates the entire universe. And every single electron in my body is merely a local excitation in that almost infinite electron field. Similarly, every proton is made up of quarks. The quarks have their own fields. When they interact together, they form bound states that appear to be protons and all. But everything is just fields, and all these elementary particles are local excitations in these fields. Now, there is something called a Higgs field. So in the 1960s, it was proposed that the universe, we did not understand where does mass come from? Why are certain elementary particles massive? Why do certain particles have more mass? Why are certain particles like the photon massless? Why is it so? So I think it was in the 1960s that Peter Higgs and a couple of other physicists put forth a theory that there is a 5th boson, which is now called the Higgs boson. And so if there is a Higgs boson, it will have a Higgs field that permeates the entire universe. And it is the interaction of elementary particles with this Higgs field that endows them with mass or not. So if some particles interact weakly with the Higgs field, then they have small masses. If certain particles interact strongly with the Higgs field, they have larger masses. And particles that simply don't interact with the Higgs field are massless. So that is what was proposed in the 1960s. The theory was constructed, made out. And in 2012, I believe, in the Large Hadron Collider, we finally found evidence that the Higgs boson does exist. Yeah, so this particle was finally discovered after a very long time in 2012, I believe. And that is the one major discovery that we have seen coming out of the Large Hadron Collider in Geneva, Switzerland. So that's what the Higgs field is. That's what the Higgs boson is. Without this particle, the universe would be a massless place. So mass itself is like a force in a way. Yeah. So that's why certain particles are more massive, certain particles are less massive. The most massive particle we know of is the top quark. Once again, let me put that on the screen. The top quark is the most massive particle that we know of, right? You can see it's 173.1 GeV. And what that is, you can look it up, what a GeV is. GeV. Okay, so that's the most massive particle, which means that it interacts very strongly with the Higgs field. There is a very interesting analogy that people have given. It's not something I have come up with, but it's very interesting to think of in this way. Let's say you have a restaurant, or let's say you have a hall, okay? A big hall in which you have lots of people. At one end of this hall, there is a bar where you can go and get drinks. And the door is at the other end of the hall. Now, when a famous person comes into the hall and they want to get to the bar, it will be hard for them to get there because everybody converges on them. Oh yeah, I'll give you. I'm a big fan of yours. Can I have an autograph? Can I have a selfie? So it'll be very hard. It'll take a lot of time for that famous person to cross the hall and reach the bar. So the hall is filled with people and they all recognize the celebrity and they all want to go and talk to them. But if a completely unknown person comes into the hall and wants to go to the bar, they will be able to go without any interaction with the crowd. So the crowd in this hall can be thought of as the Higgs field. And if you are completely unknown, you can pass through the crowd without any interaction with the field, with the Higgs field. So then you are massless. But if you are a celebrity, everybody wants to talk to you. So it's very hard to reach the bar. So that is a very massive particle and a particle that interacts very strongly with the Higgs field. So that is an interesting analogy that people have come up with, right? So that in brief is about the Higgs field and the Higgs boson. Abhijit says the bright star Sirius is roughly 8.6 light years away. Does it mean that when you see it in the sky tonight, you're actually seeing Sirius the way it was 8.6 years ago? Absolutely right. Light takes 8.6 years to reach here from that star. So what you are seeing is light that came from the star, that began its journey from the star 8.6 years ago. So if you have a telescope, you're looking there, you're seeing what happened 8.6 years ago. Yeah. You're not seeing something that's happening right now. In relativity, simultaneity is a tricky concept. It doesn't really happen. It's not really a concept that makes sense from the perspective of relativity. From special relativity, there is the relativity of simultaneity, which you can study, which means that any two events from a certain perspective can be seen as happening simultaneously. So it depends on your frame of reference and where you are and so on. But yes, from our perspective, from our frame of reference, where we are on our planet, what we see when we observe light from Sirius, we are seeing something that happened 8.6 years ago. Let's say you're observing a galaxy that is 10 million years away from here. You look at the telescope and you see the image. You're seeing light that started its journey from there 10 million years before today. So you're seeing what happened there 10 million years ago. That's how it is. Nikhil says, suppose we have a time machine and we have a pair of quantum entangled particles. We keep one here and we take one particle back to the past. Will the quantum entanglement still work? And if yes, can we say that information can travel across time? Well, okay, let's first of all understand what quantum entanglement is. A very simplistic analogy is a pair of gloves, a left-handed glove and a right-handed glove. Let's say you are sitting in the city of Bengaluru, okay, and you send one glove. Okay, let's say you are sitting in Mumbai, all right? Let's say you're sitting in Mumbai. You put one glove in a sealed package and send it to Bangalore. You take the other glove, put it in a sealed package, and send it to Berlin. So your friend in Bangalore receives one of the gloves, and your friend in Berlin receives the other glove. Now, let's say your friend in Berlin opens the glove and he or she finds a right-handed glove, then they will immediately know that your other friend in Bangalore has a left-handed glove. Now, let's say you send one of the gloves to the Andromeda galaxy and one of the other gloves to star Sirius. So when your friend on Andromeda receives the glove and sees what it is, then even though Sirius is 1.5 million light years away, he or she, your alien friend, will immediately know that your friend on the other star, on Sirius, has received the left-handed glove, right? So information seems to be traveling faster than the speed of light, which is not quite the case, but it's a system. So an entangled system is a quantum system whose wave function, which has a single wave function. That's what it is. That's how you could put it across. So when you have information of one part of the system, you immediately know what the other part of the system is like. So that is what entanglement is. So let's say, like Nikhil is saying, we have a pair of quantum entangled particle. Let's say you have two particles, one with spin up, one with spin down. They are in a state of entanglement, which means that if you see one particle, you will immediately know what the other particle's state is, right? And he says, if we keep one here, we take the other particle back to the past. Well, that is unphysical. That's where your thought experiment breaks down, because there is no way of sending anything back to the past. Time machines don't exist, right? So the thought experiment is unphysical. You're adding an element of magic to it, right? So if we were to somehow make it happen, if we were to actually invent a time machine that could take things back to the past, if that were possible, then it could mean that quantum entanglement could actually happen across time periods, back in time, etc. But it's not information traveling from one place to another. Understand that properly. What you really need to understand is that no information is traveling. There is no superluminal transmission of information. Yeah, you cannot have communications through entanglement. It's just that when you see one particle, you immediately know what the state of the other particle is, and that's all. There is no actual communication or transmission that is happening. So even if you could send one particle back in time and keep another one with you, then the person who is, let's say, 100 years in the past could know what the other particle is like 100 years in the future. Yes, but no communication is happening, no transmission is happening. So even if you could do this, information cannot travel through time. Quantum entanglement is not about transmission of information, it's not about communication of information. It's just about a single system that it is about a system of particles that has a single uh, wave function. So if you know one, you know the other, the state of the other one. That's all quantum entanglement is. Aditya says there are infinite stars in the universe, but still the night sky is dark. When we are in a rainforest, we cannot even see the sun because of dense vegetation. Then why don't we see the sky filled with stars, which are trillions in number? In other words, please explain Olber's paradox. Olber's paradox. Uh, okay, I don't know what Olber's paradox is, but let me address the question, which seems to mean Olber's paradox. The stars are not trillions in number. The approximate number of stars in the observable universe is about 10 raised to 24, 23 or 24, roughly. Give or take a couple of zeros here or there, right? So that's an insane number of stars, 10 raised to 23, let's say. Understand this. 10 to the power of 23, 1 with 23 zeros, is not infinity. It's a finite number. It's a very, very, very large number, hard to imagine, hard to comprehend, but it is not infinity. If there were an infinite number of stars in the observable universe, there would be a star sitting right here. There would be stars everywhere. Right here. I would be inside a star then. But I'm not inside a star, which means that the number of stars in the universe is not infinite. It is finite. It can be approximated to around 10 raised to 23 or 24. So, the first assumption that you have made is not correct. There are not an infinite number of stars in the universe. There is a finite number of stars. And if you look at space, from all the observational evidence that we have, from all the instruments over all of human history, we know that space is mostly empty. When galaxies collide, they're not really colliding, they're simply merging. There is no actual collision of stars ever, right? So when in the future our home galaxy, the Milky Way, will collide with the Andromeda galaxy, which is traveling towards us, which will happen in 1 billion or 2 billion years, or somewhere in between, the actual process will be a process of the merger of two galaxies. There will be no actual collision, bang, 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 of the two galaxies and the stars that they contain. They'll simply pass through each other, and there will be a gravitational dance that will take a couple of billion years or maybe longer. And eventually, there will be a larger galaxy that will emerge at the end of the process, a larger galaxy. So that's what it is. So I don't know what Olber's paradox is, but the assumption that there is an infinite number of stars in the universe is incorrect. There is a finite number of stars, and that's why the night sky is dark. If there were an infinite number of stars, the night sky would be as bright as the surface of the sun, or even brighter than that. So that is the reason why the night sky is dark, because it's mostly empty space. The stars are few and far between. Not few, but the distances, average distance between stars is of the order of light years, right? Many light years. The closest star to Earth is about 4 or so light years away. Yeah, Proxima Centauri. And the distance between our galaxy, the Milky Way, and the nearest galaxy, Andromeda, is about 1.5 million light years. These are enormous distances. So that's why the night sky is dark. The number of stars is not infinite, it's finite. All right. Origin says, don't you think that theoretical physicists have gone too much creative and radical in the past few decades? For instance, we are talking about multiverses, parallel universes, higher dimensions, holographic principle, etc. They don't have any experimental grounds. Things like the multiverse are brought up in discussions as if it's completely natural and self-evident. Do you think physicists need to be more conservative? I would very much like to hear your views on this. I think this might be to the discovery of quantum mechanics and general relativity in the 20th century. Okay, PS, I'm not sure what that is, but yeah. Have physicists gone overboard? I think they have, to a large extent. When we talk about the string theory landscape, 10 raised to 500 different universes, possible universes, etc., what's the evidence for this? We are going beyond science when we're talking about these things. Science, there is something about science that's very clear. Any scientific theory needs to be A, testable, and B, falsifiable. It has to be falsifiable. When we talk about multiverse, when we talk about parallel universes, there is no way we are ever going to be able to test it. Right? We can only observe what exists in the observable universe. The observable universe is most likely a small subset of the actual universe that we inhabit. And beyond the universe, if there is something beyond, there is no way of knowing what's out there. And there's absolutely no way of testing it or observing it. We can only observe a small subset of the actual universe. So when we talk about a multiverse, that is non-testable, that is non-falsifiable, and that means that it's not science. Yeah, mathematically you could come up with scenarios in which there could be multiple universes. Yeah, Sure, but it is not testable, it is not falsifiable, and that's why it is something that is not quite science. It is either philosophy or ideology. Yeah. And yet you have all of this becoming mainstreamed. Physicists talk about this parallel universes and things like that. Yeah, higher dimensions which we have never been able to observe. Well, higher dimensions is something that's right here, theoretically. So we could try and devise tests of whether these higher dimensions exist or not. Many of these higher dimensions are supposed to be compactified dimensions, so you can observe them only in the very small quantum domain, essentially. So maybe we could in the future test that sort of theory out. So that is still something that's within the realm of science. But when we talk about parallel universes and the multiverse, that is just that's not science, right? So yes, right now we have lost some of the discipline that science needs to have, and that's why we are kind of adrift, and we have in some way lost touch with reality. In the past 30 years there has been no new progress in physics. It's like we have hit a brick wall and we are going no further. Yeah. There are so many open problems, unsolved problems in physics, that we have made no progress in the past 30 years. The last big new breakthrough was the inflation in 1980, 81, 82, thereabouts. Yeah. After that there's been nothing new, that any new progress that has actually been tested and proven, right? So yeah, so that's why it looks like we need a change of approach. Right now there's too much groupthink in physics, in theoretical physics. Theoretical physics, essentially, especially in the West, has been taken over by the string theory mafia. They have garnered all the funding for themselves. If you want to do theoretical physics, if you want tenure track in academia, you need to do what everybody else is doing, which is research in string theory, publish dozens of papers over a short period of time, which establish your credentials, but which take physics not 1 inch forward. So that's what's happening, and the system is broken. The system is rotten. Academia has become very problematic, and that's why we are not seeing any new genuine advances in our understanding of the universe. So yes, I don't think physicists need to be conservative. I think physicists need to be wilder in their imagination, but they need to be disciplined. You can be creative, imaginative, and wild while being disciplined. What discipline? All your theories need to be testable and falsifiable. You talk about stuff that's not falsifiable, you need to shut up. Don't go there. It's pointless. It's pointless. I always say don't mix philosophy and science. Don't mix religion and science. Don't mix spirituality and science. These things don't mix. So that is the discipline scientists need to have, and that's kind of broken right now to a certain extent. So yeah, that needs to be brought back, and so yeah, that's one of the major problems we are facing right now in physics. Vishal says, what is the Barber paradox? The Barber paradox. It's a logical paradox. Let me try to remember what it is. It says, there's a claim, you make a claim that if you are a barber, you shave the people who are not barbers and who don't shave themselves. Okay. A barber, so this is a claim that is made. Okay. A barber is a person who shaves those people who are not barbers and who don't shave themselves. Two components: people who are not barbers and people who don't shave themselves. The combination of these two criteria. So if you are a barber, you're shaving people who are not barbers, first of all, and who also don't shave themselves. So that's what a barber does. But that means that the barber doesn't shave himself because he's a barber. So I am a barber. Let's say I am the barber we're talking about. Let's say. So I am a barber. I shave people who are not barbers and people who don't shave themselves. So That means that I don't shave myself. I only shave others because I am a barber. But that means that I fulfill one of these two criteria, right? We are already making the presupposition that I am a barber. So that is what's called a logical paradox. And the solution is very simple. Such a barber doesn't exist, right? So that is the barber paradox, which seems to be an unresolvable paradox, but this solution is simple, that the assumption itself is incorrect. Such a barber simply cannot exist. Yeah. So that is what the barber paradox is. Sudeshna says, do scientists need to recall and remember every formula or derivation they learned while doing research or study? I always wondered, can a scientist crack the IIT in 2 minutes, or do they also need to scratch their brains thinking and solving tough problems? Because whenever I try to remember all the formula and derivations of class 11 for JE, sometimes I become mad, but I am more or less very good in math. I don't have such infinite recalling ability of all formula and derivations. See, scientists don't need to memorize all the equations and all the formulas. You ask me to write down the Navier-Stokes equation, I probably will make some mistake in that, right? Uh, but if you ask a fluid dynamics researcher to write down the Navier-Stokes equation, that person will do it immediately. He or she could do it in the sleep. Yeah. You ask me to write down other equations, the Schrodinger equation, the Maxwell's equations, I could do it in my sleep. So it depends. There are certain things that you use as tools on a daily basis. Those will be burned deep into your memory. But physics is so vast. It has so many subfields. You ask me about condensed matter physics, I will remember next to nothing right now. You ask me about fluid dynamics, yeah. So that's how it is. The thing is this: when you use certain tools, certain equations, certain techniques, certain mathematical things are tools that you use on a daily basis, that you don't need to memorize. It will be there it will be burned into your brain because of repeated use again and again and again. So when you're an active scientist, when you're an active physicist, you will remember stuff that you use on a daily basis. But other stuff you can afford to forget, right? Uh, so scientists don't need to recall and remember every formula, every definition, every equation they learned while studying, while as students. But the thing is this, that when you want to become a scientist, you have to go through the JEE. If you want to go into engineering, into the IITs, there is the physics GRE for people who want to go to international institutions and all. In these exams, you have to memorize vast quantities of facts, of equations, of formulae, and so on. And you have to memorize all kinds of different techniques of solving problems on the spot within a certain time period. There's a time pressure, and you have to memorize things. So what you're actually learning is how to pass exams. Even the GRE, to some extent, is not really an indicator of how good of a physicist you're going to be in the long run. But it does indicate. So if you do well in the IIT JEE or in the physics GRE or whatever other GRE, it indicates that you are a person who is capable of a sustained period of focused, dedicated hard work, which is a sign of conscientiousness, which is one of the qualities that a good scientist must have. Right. So that's how it is. The Indian academic system is broken. You have to memorize stuff and pass exams, and you don't really learn anything. But in the case of these high stakes exams like the IIT JEE, the physics GRE and other GREs, etc., there is an element of some of that actually matters. So that's how it is. That's just how it is. That's the way the system is built. It actually proves that you are capable and you are willing of being disciplined. You're capable of being disciplined. You're capable of putting in a sustained period of really intense and hard work of memorizing all these things and solving lots of problems, which is a good indicator of long-term success in life. So that's how it is. It is something you have to do. So you got to do it. Manmat Tiwari says, my sister is in class 7th. Her physics teacher recently in a unit test deducted 3 marks for writing units in the form of this with the caret cm squared instead of square cm. 3 marks for this. It makes me wonder that whether we are able to reform the system, education system. How will we reform the teacher's mentality? Um, you're right. I have come across such teachers. I remember when I was in what standard? Seventh or something. I had to draw something on. You had to pass exams. You had to draw diagrams. It was a diagram of some kind of apparatus in physics that had to do something with sunlight. And in the textbook, it was drawn in a certain fashion. I did not memorize the thing. I understood it conceptually, and I drew it in a different configuration and a different orientation, but which made perfect physical sense. And I lost 5 marks because my teacher said, "No, that's not how it is in the textbook." Most teachers, well, I don't want to be rude. I would say that most teachers are idiots, which is true. Most of them are well-meaning. This is the way they studied stuff. That is what makes sense to them, and that's why they think that if you don't replicate things exactly the way they're in textbooks, then you're doing something wrong. When you don't replicate what's in the textbook, but you give the right answer, it means that you are actually capable of thinking. But this education system emphasizes obedience and memorization, not actual critical thinking. And that's the main problem in the education system today. So if we are to reform the education system, we will have to reform the teachers as well. And beyond a certain age, after a certain age, let's say 35, 40, most people are not capable of changing. So yeah, we will have to bring in new teachers. The best teachers will be the ones who are in the 20s, who are capable of changing, who are capable of learning. We need to, when the reforms are done eventually, we will have to retire most of the existing teachers. There's no way around it, unless they are willing to change and bring in fresh minds and fresh blood. So yes, that is something that will have to be done. With the current crop of teachers, we will not see changes. Their minds are still the same, the mentality and attitudes are still the same, and that's going to be problematic. So when reforms are done, we will need younger people to come in, people who are receptive to change. So that's what needs to happen eventually. Saurav says, as a scientist yourself, do you view the Indian academy? How do you view the Indian academia in its present state? I've witnessed an obsession with H-index scores amongst our academicians. There's a stiff obsession with grades, number of papers published, publications in reputed journals, etc. On the other hand, our institutions' research outputs are still meager and namesake. Have the elite Indian institutions only become high-salaried workforce providers, or is there still a hope for quality research coming out? So I've gone into detail about these things in episode 30, 31, thereabouts. Yeah, Ask Abhijit, a long time ago. I mean, about a year or so ago, in which I've spoken about this in detail. But let me address your question. How do I see Indian academia? Indian academia is the epitome of mediocrity. That's what it is. Forget about what you're saying. In most colleges and universities, there is no emphasis on research at all. Nowadays, I think the UGC, this obsolete thing, institution, organization, has mandated that there needs to be a certain amount of research output. So you have these third-rate research journals that have cropped up like mushrooms everywhere, in which you can essentially get some research paper published for a fee. So that's the new scam that's going on in Indian academia. All these so-called research journals that have cropped up, it's a farce. The Indian academic system is a farce, and even in the top level institutions, the top 10% or whatever, they do publish. It's publish or perish. But what's the quality? What's the output? Are they doing any real research? No, they're not. I would say about 2% or 3% of the academicians in India would be like world class. 97-98% would be mediocre, people who have no interest in research, who have no interest in progress. They're just in it for the salary and for the job security. That's how it is. So it's a morass of mediocrity. I know it very well. I've spent most of my life in the academic system. I know it intimately. I've gone through the grind. It's terrible. It needs to be changed wholesale. And when the changes happen, when the reforms happen, the current lot of academicians needs to be retired with whatever pension they would acquire otherwise, and let them go. And we need fresh blood into the system. Whenever the government decides to reform the system. Eh, so yeah, that's what it is. An amazing Indian citizen says that you have said that in order to become good at physics, mathematics, chemistry, etc., we need to solve lots of problems. Yes, I have said that. But what to do when you are unable to solve a problem? Do you directly jump to the solution, or do you try solving it again? Think about it this way. Let's say you're a sports person, yeah. Let's say you're playing cricket, and you need to take 10 wickets to win the match. Let's say you're a bowler, fast bowler, and you're in a team with five other guys or girls, whatever, yeah. You need to take 10 wickets to win the match. And consistently, you're able to only get 5 or 6 wickets and you keep losing. What do you do? So you know how to bowl, but you don't quite have the skills of how to get certain people out. So you need to acquire those skills. You need to look at what you're doing wrong. Whether you're doing something wrong mentally, whether you're doing something wrong biomechanically, whether you have the wrong strategy. So when you are unable to solve a problem, you have to step back and analyze where you are going wrong. What skill do you lack? Problem solving is a bunch of skills. It's a toolkit that you have, mathematical toolkit in physics to solve problems, right? So maybe you're deficient in one of the mathematical aspects. Maybe you're not good at calculus. Maybe you're not good at differential equations. Maybe there are certain classes of differential equations you can solve. Maybe you're bad at linear algebra. Maybe you don't quite know how to use matrices. Whatever, right? Figure out where you're going wrong, and then work on that. Address that deficiency. That's simply how it works. You can jump to the solution, but that will teach you nothing. The best way of learning something is failing repeatedly, then stepping back and looking at why am I failing. And then once you identify the reason why you're not able to solve the problem, you identify that, and then you work on that skill, and then you'll be able to solve it. And of course, it helps to eventually go and look at the solution and see how did they go about solving the problem, and so on, right? So you have to be patient, but you have to be proactive. You have to move fast. You have to identify your deficiencies and weaknesses and work on them, right? So that sort of conscious practice, if you do, you'll be able to progress. Abhijit Verma says, do you like the TV series The Big Bang Theory? There used to be another comedy series called The Third Rock from the Sun. How did you find the humor in that? Among the dramas, how do you rate Star Trek? And which other series do you recommend for scientists with a thinking and funny bone? I used to like Star Trek, the initial original one with William Shatner as Captain Kirk. That was nice. I used to like that. I saw it when I was, teenager or something. I liked that, the first run with those characters. The Big Bang Theory was funny. People actually think physicists are like that, like the guy Sheldon Cooper, right? I think the first season was funny. The first couple of seasons were quite funny. Then it got kind of stale, which was unfortunate. Third Rock from the Sun, I remember watching a few episodes when I was a kid, I think. That was quite funny, yeah. So I rate the original Star Trek series quite highly. There was something called Star Trek The Next Generation from the 90s, I believe. That was also quite good. And that took a couple of seasons to get into its stride, but it was quite good afterwards. So, and what series do I recommend for scientists with a thinking and funny bone? I'm not able to think of any interesting science fiction or such series right now. I quite like the movie Interstellar. It was reasonably well grounded in physics, and the story was also quite good. And among TV series, I can't think of any science fiction series right now. But how about I think about it and I get back to you the next time? Yeah, right. Okay, so that brings us to the end of today's questions. Let's take a look. If you have some questions, ask me now on the live chat, and maybe I'll take a few questions right now. So go ahead and ask me questions. Black Mirror. Black Mirror is an interesting one. I had seen maybe 1 or 2 episodes of that. That was interesting, yes. I don't quite have the time to watch TV series and all that, but yeah, Black Mirror was interesting. I'd seen a couple of episodes of that. Uh, is homeopathy a pseudoscience? What are its origins? I believe homeopathy originates in 18th or 19th century Germany, I think, and it is very definitely pseudoscience. Um, there is this term called a homeopathic dose. A homeopathic dose of anything is an ineffective dose, a very, very incredibly dilute dose. Yeah. So homeopathy is, I don't remember exactly what the tenets and the principles of homeopathy are, but what I do know is that the dosages of whatever active substances are used are so incredibly low that they are never going to work. And there is this something called there is this concept, I believe, of water retaining memory of stuff, of water retaining memory of what substance you put in it, and then the water itself is going to work for you, or something like that. And these concepts or these ideas have no basis in actual science, right? So overall, what I can say is that homeopathy is indeed pseudoscience. In India, most people club homeopathy with Ayurveda, which is incorrect. Ayurveda is actually something that has active ingredients, herbal ingredients, which have not been studied well, but whatever is studied seems to work. For instance, Brahmi, it is now used in nootropic combinations. Brahmi is a plant. It's a herb that enhances cognitive function, and that seems to be proven, right? And there are lots of other herbs, Arjuna, for instance, and so on. Yeah, in Ayurveda, that scientists thus far have kind of refused to study in detail, but they have been tested over thousands of years. So Ayurveda is not pseudoscience, but homeopathy certainly is, right? Okay, do we have anything else? Uh, if the universe is expanding, can there be a chance of forming a new galaxy every day, every week, every month, every year, every second? Um, a galaxy formation, I think it's something that takes a much longer time than the process of forming stars. Uh, when did the first galaxies form? Uh, the James Webb Telescope, which is currently in operation, recently gave us an image of the oldest known galaxy, which dates back to about roughly 250 million years after the Big Bang. So it's clear that galaxies formed very quickly after the initial Big Bang expansion, 230, 250 million years after the Big Bang. So galaxies seem to have formed in the earlier phases of the universe, when the universe was much smaller, and when stars were they were close together. And yeah, so I don't know if we see any galaxies actively forming right now. We do see stars actively forming. There are certain regions, stellar nurseries in various regions of space within our own galaxy, in other places as well, where stars you can see them actively forming. You can see protostellar disks, you can see planets forming and all. But as far as I know, we don't see any galaxies forming from clusters of stars and all that. Yeah, so it looks like the chance of forming new galaxies is something that has not been calculated. The rate of formation of galaxies, we don't see any actively forming galaxy right now. It's an interesting question that you asked, and I don't quite have the answer to it. As far as I know, we don't have any number for how many for the rate of the formation of galaxies. We know at what rate stars form, but not galaxies. And as far as I know, there is no actively forming galaxy that we are aware of right now. Interesting question. Okay, let's take some other questions if we can. Are multilingual people more intelligent, and how many languages can I speak? It is believed that multilingual people they perform better on intelligence tests and cognitive tests, and the brain develops differently. Yeah. So if you are multilingual, if you make the effort of learning more than one or two languages, it kind of helps you cognitively, and maybe it contributes to a higher IQ, or a higher intelligence overall. Yeah, that's possible. How many languages can I speak? Four at least. And there are certain languages that I can speak. I can throw out a few phrases of some languages here and there. It's all based on language families. So if you know one language, you can kind of understand other languages that are closely related to that. If you can speak Hindi well, most languages in northern and western India will make sense to you. If you can speak any of the Western European languages, most of the languages in that region could be somewhat intelligible to you, and so on. So I can speak four languages properly, and other languages here and there I can throw out a few words or phrases. Yeah. All right. Newton or Einstein, both both made significant contributions in their own right. Yeah. Okay, please don't ask me questions about history today, my dear friends. Today is about science. Um, let us see. Do we have anything else? Okay, Louis says, if we can see the past of stars when we observe the night sky, firstly, can we theoretically at least see our own remote past of the sun and of our planet? Well, it depends on where we are. So if we are sitting here and we are observing the Andromeda galaxy, we are seeing light that began its journey from there 1.5 million years before today. So we are observing the past of the Andromeda galaxy. If we are looking at the sun, we are seeing light that emerged from the sun 8 minutes ago. The distance between the Earth and the sun is 8 light minutes. It takes light 8 minutes to travel from the sun to the Earth. So we are seeing the past of the sun itself. So the question is, can we theoretically see our own remote past? Theoretically, if you were to teleport yourself to the Andromeda galaxy and you were to observe the Earth from there, you would be observing something that happened 1.5 million years in the Earth's past. So, so maybe you could see the ancestors of humanity if you could somehow teleport yourself there. And we don't have any means of doing that. But theoretically, if you were there, then yes. So theoretically, if I could make a spaceship or wormhole that would instantaneously take me there to some place in the Andromeda galaxy, and then if I would observe the Earth, I would be seeing what happened on the Earth 1.5 million years before today. The early humans, that had just split off from our chimpanzee cousins and so on. So theoretically, it is possible, but practically, unfortunately, we don't have the technology or the means of making that happen. So it depends on where you are located. So in that manner, we could possibly see our remote past of our planet and our solar system. Okay, my friends, that's the last question for today. We are done for today. 2 hours crossed. Thank you very much. Always great fun talking to you all. And I will see you in tomorrow's live stream, which will be about other topics. All right. Thank you very much. Take care. Stay healthy. And I will see you in the next episode. Bye.